All right, so we're starting with a little bit of review on simplifying logarithms. Now, the first thing when simplifying that first one is that I notice that we have that 2 out front of the logarithm. So the very first thing I'm going to want to do is I'm going to want to put that into the logarithm. Now, remember that a number that's multiplied out front becomes an exponent. So really this first one's going to become log base 4 of 6 squared. And so then we actually do the 6 squared. So at this point, we now have log base 4 of 36 minus log base 4 of 9. Now that I've done that, I can take care of the subtraction. I can go ahead and do the writing it as a single logarithm at this point. Now, when I subtract the logarithms, what does that become within a single logarithm? Division. Yeah. So this is going to be log base 4 of 36 divided by 9. Now that happens to be a nice pretty number. What is 36 divided by 9? That's going to be 4. So then this boils down to be log base 4 of 4. All right. Can we simplify this any further? Is log base 4 of 4 a nice pretty number? Well, you actually can know that without even using your calculator. Because remember how we read logarithm. Log base 4 of 4 is really saying 4 to the power of what equals 4. Is that a nice pretty number? Should be. Should just be 1. Because anything to the power of 1 is just itself. And then we go on to the second one, and we're going to approach it the same basic way. So again, I have that 2 that's out front of the logarithm, so I'm going to want to deal with that first. So that's going to become log of 7 squared. And then I can actually do the 7 squared. So that gives me log of x plus log of 49. Now I can go ahead and make that a single logarithm, deal with the addition. What does the addition become when I change it into a single logarithm? Multiplication. Yep. So this becomes log of 49x. So when we look at that, can that be simplified at all? Well, log of 49 is not a nice pretty number. And so because of that, and certainly log of x isn't going to become anything else, we're just going to have to leave it then as this being our final answer. So this one didn't simplify any further, so then this is as good as it gets. All right, now next up, we're going to go back to some of our compounding interest stuff. So to start with, we're going to be taking a look at this problem. So suppose the population of wolves is decreasing at a rate of 8% annually. If the initial population of wolves is approximately 5,000, after how many years will the population fall below 3,000? So we're going to see how to approach this. This is theoretically just review. So go ahead and see if you can do this entire problem start to finish. Remember, start by writing out the equation though, and then use it to find your answer. Once we get it to this point where we have the exponential by itself, now we need to remember how do we solve for an exponent. And solving for an exponent is the entire reason why logarithms exist. So the first thing I want to do in solving it from there is turn it into a logarithm. So I'm going to have to be figuring out what log base 0.92 of 0.6 is. In order to calculate that value, you have to use the change of base formula. So we do log of 0.6 divided by log of 0.92. Once you do that calculation, so now that we practiced our little bit of review here, dealing with stuff that we've done before, now the next question is, what happens if we're not compounding our interest annually? Because all the stuff we've been doing before, the interest is compounded once a year. Like in that wolf problem, the same thing. It was compounding annually. Well, there is a variation that we can make. So if we go back to our annually compounding interest equation, this is the same equation that you already have in your notes. We're going to tweak this a little bit to allow us to go by month, compounding by week, or something like that. So we now add some complexity to this equation. We're now going to make this an equation that we can use if the interest is not compounding annually. So first up, add this into your notes, and then we'll see how we can actually apply it and use it. All right, now a little note here about how do we use this equation, this version of it. N is the number of times we compound the interest per t. So that's going to generally be per year, because normally this is dealing with annual interest. So for instance, if I wanted to figure out what happened if we compounded the interest monthly, N would be 12, because you're compounding it 12 times a year. If we compounded it quarterly, sometimes you'll see that with financial applications, quarterly compounding interest would mean you're doing it 4 times a year, so N would be 4. Semi-annually means you're compounding it every 6 months, so in other words, twice a year. So there are just some different variations. Now we're going to take a look at this as an example problem about how this would all get put together. So in our example here, you invest $1,000 in a savings account that pays 1.2% per year, but interest is compounded monthly. And then what will the value of the account be in 5 years? And so because I'm being told here that I'm compounding monthly, that's what tells me that I'm using this new version of the equation, because I'm going to have an n value that's not just a 1. Basically, this is the same equation we've always been using, but if you're compounding annually, n is just 1, so that's why we didn't have to account for it. So to build the equation then, for this particular scenario, I'd say a of 5, because I'm looking for the amount after 5 years, equals 1,000, because that's our starting value. Then times 1 plus, turn the 1.2% into a decimal, just like we always would. So 1.2 divided by 100 is 0.012. And then that's over n. And in this case, since it's compounding monthly, that means I'm compounding it 12 times a year. So that's why we got it over 12. N is 12. And then in the exponent, n is still 12, just as it was. And then that's times t. In this case, we're looking to see what happens after 5 years. So if I'm then going to use this equation to figure it out, I'm going to want to do a little bit of simplifying first. So that's going to give me a of 5 equals 1,000 times 1.001 to the 60th. All I did here is I did that division, which gave me 0.001, and then added that to the 1 over here. And then I did the 12 times the 5 in the exponent to get the 60. You want to do that part first, because then this is much more straightforward to calculate. Now it looks like what you've always been doing. So then we can go ahead and do that calculation. In doing so, I do the 1.001 to the power of 60, and then multiply that by 1,000. So in this case, that would happen to give us $1,061.80. Now, a little side note on that. This is a case of compounding monthly, just so you can see how that would compare. What would the number have been if we weren't compounding monthly? What if it was annually like we've done in the past? If we had done it for annually, in other words, n being 1 using the equation we had before, you would have ended up with an answer of $1,061.46. So it's not a huge difference by compounding it monthly, but it did make a difference. So notice that by compounding more often, we actually ended up with more money in the account. So the more often that you compound the interest, the better it is for you, assuming that, of course, you are the one earning the interest. All right, so we've seen one example of it. Now we're actually going to go and start doing it where you can actually practice it, doing it on your own and then checking it. So you're going to want to write down the key points of this problem. In this case, when your nephew is born, because you're a good aunt or uncle, you put $200 into an account for him that will pay 6% interest per year, compounded daily. How much will that investment be worth in 20 years? All right, so let's see how you go about building this equation now. We start, of course, with a of t. Now, in this particular problem, what is our t value? Well, we're looking to see what it is after 20 years, so It is 20. So we start with a of 20 equals. Next up, the p-value, principal. What are we starting with? 200, yes. We're starting with this original 200 that was in the account. Now we have to get into that whole parentheses 1 plus r thing. Now, in this case though, remember, it's not just r that I'm putting here. It's going to be r over n. So in order to figure out r, I take my percent and I divide it by 100 to turn it into a decimal. That's going to give me 0.06. Then that's going to be over n. In this case, what is n? 365. Because we're going based on 365 days per year. Yes, some of you might be going, well, what about leap year? We're ignoring that, okay? Because we don't really want to have to deal with that level of complexity, right? So we're just going to call it 365. Now, I go into the exponent. In the exponent, we have n times t. N is still 365. Whatever is on the bottom of that fraction is the same number that you put in your exponent. It's the same n value. And then that's going to be times t. And we already figured out what t was, remember? That was 20, because we're looking to see what it is after 20 years. And then we go and we need to go and find this value. So first up, when finding the value, we want to actually do the 1 plus this 0.06 over 365 and get that number. Now when we do that in this problem, it's not a really pretty number. In fact, it's 1.00016, and then that decimal just keeps on going on and on forever. When you go and do this calculation where you actually raise it to the power of 7,300, you are going to want to use that whole decimal. So make sure that you are actually using the entire decimal that your calculator gives you when you raise it to that power. Because when you multiply something by itself over 7,000 times, a little difference can make a big difference later. Because that's multiplying a lot together. All right, and then we go ahead and do that operation. If all has gone well, you're going to be getting an answer of $663.96.